Okay, so hi everybody. So today we're going to go ahead and start on 4.8, which has to do with rank, nullity, and fundamental matrix spaces. Okay, so we'll just jump right into it. It's got to focus it a little bit better than what it is. Okay, so about right there. Okay, so here we go. So the row space and column space of a matrix A have the same dimension. Okay, so that's the theorem that we're going to be dealing with here. Okay, so we're going to prove this. So proof. Okay, so we're going to let R be any row echelon form of A. So from theorem 4.7.4 and 4.7.6b, and I'll let you guys go back and look that up. Pause the video, go back and look that up. Okay, I know that the dimension of the row space of A is equal to the dimension of the row space of R, okay, the row echelon form of it. Furthermore, I know the dimension of the column space of A is equal to the dimension of the column space of R. Okay, so what I want to try and do is I want to show that these two actually have the same dimensions, but I'm not actually going to show those two. I'm going to go through and show that these two have the same dimension. Okay. So we know that the dimension of the row space of R is just the number of leading ones in the matrix R. Okay. And by theorem 4.7.5, once again, go look that up. The dimension of the column space of R is also the number of leading ones. Therefore, our conclusion is that the dimension of the row space of A is equal to the dimension of the column space of A. Okay, and we're done. Okay, we showed that these two are equal to each other, and since this is equal to that one and this one's equal to that one, those two must be equal to each other as well. Okay, so definition 4.8.1, the column dimensions of the row space and column space of the matrix A is called the rank of A, and it's denoted rank of A, and the dimension of the null space of A is called the nullity of A, and is denoted nullity of A. Okay. Okay, so what we're going to do is we're going to go down here. We're going to find the rank and nullity of this matrix. Okay, so if I have this matrix here, and I'm going to deal with I'm going to use this as matrix A, and I'm going to put it into the system of equations ax is equal to b, then what I know, this thing will reduce to, matrix A reduces to, let me write that out. You have 1, 0, negative 4, negative 28, negative 37, 13, 0, 1, negative 2, negative 12, negative 16, and 5, and then everything else is zeros. So the last two rows are uniformly equal to 0. Okay, putting this into this system then, actually equal to 0. We're going to do the homogeneous case first. Okay, putting that into the system, then I know what I have is I have x1 minus 4x3 minus 28x to the fourth minus 37x to the fifth plus 13x to the sixth is equal to 0. And I also have x2 minus 2x3 minus 12x4 minus 16x to the fifth plus 5x to the sixth is going to be equal to 0. Okay, and now what I'm going to do is I'm going to come up with a general solution for this. So I'm going to let x3 be equal to r. I have x4 is going to be equal to s. x5 is going to be equal to t. And x6 is going to be equal to u. And then plugging that into these equations and solving for x1 and x2, I have x1 is equal to 4 x3, but that's r, plus 28x4, but that's s, plus 37x5, but x5 is t, and minus 13x is 6, which is u. And then I also have x2 is going to be equal to, so adding everything over, so I have 2r plus 12s plus 16t minus 5u. Okay, and this right here is going to represent what our general solution is going to be. Now, what is the nullity? Okay, the nullity is the dimension of the null space. So you remember that actually happens to coincide with the number of free variables. So how many free variables do I have here? 1, 2, 3, 4. So the nullity of matrix A is equal to 4. Okay, next page. Okay, so what is the maximum possible rank of m by n of an m by n matrix A? I'm not sure why I have that extra thing in there. Okay, so since the row vectors of A lie in Rn, I know it's a little confusing because when you think of this, this is the rows by the columns, but you're going to have m rows by n columns. And so what that means, in each one of the rows, you're going to have n elements. So since you're going to have n elements, then each row vector lies in Rn, and the column vectors of A lie in Rm. Then the rank of A is at most the smaller of m and n. So the rank of A has to be less than or equal to the minimum value of m and n. Okay, that's because if you have more matrices than what the normal span of it would be, like the size of the dimension would be, then there has to be some redundancies. So you just have to go ahead and eliminate it down to that. Yeah. Okay. So theorem 4.8.2. If A is a matrix with n columns, then the rank of A plus the nullity of A is equal to n. Okay. So proof here. It's kind of a loose proof here. It's kind of more of a talk through. So since A has n columns, then the homogeneous linear system AX is equal to 0 has n unknowns. Okay, which we can break apart into, we have the number of leading variables. And in the prior example, that was like x1 plus x2. Sorry, x1 and x2. Okay, plus you take the number of free variables and that has to be equal to n. Okay, and that's it. So therefore, this right here is the rank of A plus the nullity of A is equal to n. Okay, and there we are. Okay, so going down here, we have this matrix. We notice that it has 6 columns, and therefore n is equal to 6. So we have the rank of A plus the nullity of A is going to be equal to 6. Now, we know from example 4.8.1 that the rank of A is equal to 2. So plugging into that formula, then I know the nullity of A must be equal to 4. Okay, it's pretty simple. Okay, theorem 4.8.3. If A is an m by n matrix, okay, m rows, n columns, then the rank of A is the number of leading variables in the general solution of A of x equal to 0. And the nullity of A is the number of parameters, free variables, in the general solution of AX is equal to 0. So in this example right here, example 4.8.4, find the number of parameters in the general solution of AX equals 0 if A is a 5 by 7 matrix of rank 3. So we know we have the rank of A plus the nullity of A is going to be equal to n, and in this case you have 7 columns, so it's equal to 7. So you have 3 plus the nullity of A is equal to 7, so the nullity of A is equal to 4. Okay, and there we are. Okay, next page. Okay, so the next page should look pretty familiar, at least most of it, all the way up until I believe G we've had before. These are the equivalent statements. That means if this is true, then any of these other ones are true. So all we're going to do now is we're going to add some more to the list here, okay? So the first one, the column vectors of A are linearly independent, okay? So if any of these other ones are true, then that's to be linearly independent. There's a mistake in I. It should say the row vectors of A are also linearly independent. Okay, the column vectors of A span Rn. The row vectors of A span Rn. The column vectors of A form a basis for Rn. The row vectors of A form a basis for Rn. A has a rank of n. Okay, and that should make sense because the rank is the dimensions of the row or column space. You can see here the column vectors form a basis of Rn, so therefore it has a dimension of n, therefore A is a rank of n. And then A has a nullity of 0. That has to tie back into what would be only the trivial solution here. Okay, theorem 4.8.5. If Ax equal to B is a consistent linear system, so it has at least one solution, of m equation and n unknowns, and if A is of rank R, then the general solution of the system contains n minus r parameters. Okay, so we're going to prove this. So looking back, so by theorem 4.7.2, the number of parameters is equal to the nullity of A, which by theorem 4.8.2 is n minus r. And so we're done. Okay? And that's it. Okay, so I kind of goofed up for this next one because I actually forgot to put in the theorems. Instead, I just put in the proofs. So there's going to be a lot of writing here. We really have to try and write small to get it all in. Okay, so this has to do with an overdetermined case and an underdetermined case. So in other words, there's going to be some times where you have, say, 5 variables, but I only can come up with 3 different equations for those 5 variables. Now, what you guys know from general algebra is that system is not always solvable, right? You can't always find a unique solution because you need at least as many variables as what you have equations. On the other hand, what happens if you have too many equations? You only have 3 variables and we have 15 equations. Then there's going to be some sort of redundancy there. So that's what this has to do with. So we have 2 different things here. We have the overdetermined case and we have the underdetermined case. Okay, so A. This is going to be the overdetermined case. Okay, so if m is greater than n, then the linear system Ax is equal to b is inconsistent for at least one vector B in Rn. Okay? So we have more rows than we have columns. Okay, that means we have more equations than we actually have variables. Okay, so let's take a look at this. So proof. So we're going to assume that m is greater than n. Okay. Therefore, the column vectors of A cannot span Rm. All right, you need at least that many to span it. So if you have n vectors trying to span m dimensions where n is less than m, you can't do that. You can't possibly span it. Okay. Thus, there is at least one vector B in Rn, m, that is not in the column space of A. And for that system, Ax is equal to B is inconsistent by theorem 4.7.1. Okay? And once again, you should go back and look that up. Okay, so that was the overdetermined case. What about the underdetermined case? Okay, so underdetermined case. Okay, so this is if m is now less than n, then for each vector b in Rn, the linear system Ax is equal to B is either inconsistent or has infinitely many solutions. Okay, and we're going to prove this as well. Okay, so this is kind of cool how it works. Okay, so you have an if-then statement, right? You have this thing that you can assume, and then you have to prove the rest of it. Well, what am I trying to prove? I'm trying to prove that it's inconsistent or it has infinitely amount of solutions. Okay, so the first thing we should note is any system is consistent or not, right? It's either consistent or it's not. So if the system is inconsistent, then we are done, right? Because it's either that or that. Okay, so I just basically showed that that was the case. Now let's assume that this is not the case, therefore it's consistent, and then that will lead us to this conclusion that there's an infinite amount of different solutions. Okay, so we then assume that the system is consistent. So therefore, by theorem 4.8.5, we know the general solution has n minus r parameters. By the way, how do we show that it's an infinite amount of solutions? You show that it has parameters. Okay, that's what we have to show. So because if it has a parameter, which means you can plug in any value for it, 1, 2, 3, 4, whatever, and it will give you a solution. So this has n minus r parameters. So to show that it has parameters, which I know I just said it does. I just need to show that this doesn't equal to 0, or for that matter, it's a positive value. So I just need to show that that's positive. Okay? But the rank of A is the smaller of M and N. So therefore, we have N minus R, which is what I'm trying to find, is equal to N minus M. But under this case, since N is greater than M, I know that that's going to be greater than 0. Okay, which implies there are an infinite number of solutions. Okay, there we are. Okay, next page. Overdetermined and underdetermined systems. Okay, so what can you say about the solutions of an overdetermined system Ax equal to B of 7 equations and 5 unknowns? So 7 equations, that means we have a 7 by 5 matrix. Okay, so solution to A. Okay, the system is consistent. That's because I have at least that many equations for some vector B in R7. Now, why R7? Because if you look at the system AX is equal to B, this has to be of dimension 7 by 1. This is a 7 by 5 matrix. This is a 5 by 1 matrix. So the solution is going to have a 7 by 1 matrix. Okay. And for any such B, the number of parameters in the general solution is n minus r, which is equal to 5 minus 4, which is equal to 1. So there we have it. Okay, n was equal to 5 because that was the column. We know what the rank was. It was 4, so just plug it in, you get 1. Okay, and then B, so to prove B, the system is consistent or inconsistent. Okay, it depends on the equations. Okay, we have fewer equations, we have variables now. But if it is consistent, for a vector B in R5, then the general solution is n minus r, which is equal to 7 minus 4, which equals 3 parameters. Okay? So that time I had fewer equations than what I had variables. Okay, so consider this linear system. So we have this, which I can write as a system of equations, right? And if I augmented it, it'd be 1, negative 2, B1, 1, negative 1, B2, 1, 1, B3, 1, 2, B4, and then 1, 3, B5. Okay, that's what it is augmented. Reducing this using Gauss-Jordan elimination. So using Gauss-Jordan, this reduces to 1, 0, 2b minus b, 2b2 minus b1, 0, 1, and this is b2 minus b1, and then these are all zeros, and this one's going to be b3 minus 3b2 plus 2b1, and you have b4 minus 4b2 plus 3b1, and the last one is b5 minus 5b2 plus 4b1. Okay, just reducing that. Okay, now if I was to take this and write this in the system, ax is equal to 0, what I get then is I would come up with the equations. And the equations would simply be 2b1 minus 3b2 plus b3 is equal to 0. Just based off of that one. I also have 3b1 minus 4b2 plus b4 is equal to 0. And then 4b1 minus 5b2 plus b5 is going to be equal to 0. Okay, so those would end up being the three free variables. Okay, so what I know then, this will yield then the solution b1, which is equal to 5r minus 4s, b2, which is going to be the equation 4r minus 3s, b3 is the equation 2r minus s, and b4 is the equation r, and b5 is the equation s. Okay. However, the column matrix has two columns. Therefore, n is equal to 2. And it has a rank of 2. But because there are two non-zero rows in reduced row echelon form, it doesn't have to be, it is reduced row echelon. Okay, this implies the system is consistent and its general solution contains n minus r, which is equal to 0 parameters. Okay, so therefore the solution is unique. Okay, next page. You got 2 pages left, kind of. Okay, so we got some things going on here. Fundamental spaces of a matrix. Okay, so we basically start working with matrices, and now that we're working with these matrices, now we're deciding, and then we define subspaces. Now we decide, okay, what are the important subspaces? Okay, so what we know is there are 6 important vector spaces associated with matrix A and the transpose of A transpose. Therefore, the row space of A, the row space of A transpose. The null space of A, the column space of A transpose. The null space of A and the row space of A transpose. But here's what I know. I know that these two right here are really the same thing. And then these two are really the same thing. Okay, so but since the row space of AT is the same as the column space, because it's the same exact vectors, it just has been flipped. And then vice versa, we know we can reduce these 6 into 4 equations. So really all I'm concerned with now is the row space of A, the column space of A, the null space of A, and the null space of A transpose. Okay, so those are the things that I'm really worried about. Okay, so theorem 4.8.2, if A is any matrix, then the rank of A is equal to the rank of A transpose. Okay, I'm not going to go through and prove this. I'm just going to talk about some key points here, okay? This theorem has important implications. Okay, so if A is a m by n matrix, then the rank of A transpose is equal to the nullity of A transpose, which I know is equal to M. Okay, so this theorem implies this. Okay, therefore, I know the rank of A, because the rank of A is the same thing as A transpose, is equal to the nullity of A transpose, which is equal to M. Okay, which allows me to express the dimensions of all 4 fundamental spaces in terms of the size of rank of A. Okay, so what do I mean by that? I know that the dimension of the row space of A is equal to R. I know the dimensions of the column space of A is also equal to R. I know the dimension of the null space of A is equal to n minus R. And I know the dimensions of the null space of A transpose is equal to M minus R. Okay. Almost done here. So definition 4.8.3, if W is a subspace of Rn, okay, so it's a subspace of Rn, then the set of all vectors in Rn that are orthogonal to every vector in W is called the orthogonal component of W, as denoted by the symbol W with that upside down T, which represents perpendicular or orthogonal. Okay, orthogonal, remember here, is perpendicular. Okay, so theorem 4.8.8, if W is a subspace of Rn, then W, the orthogonal component of W is also a subspace of Rn. Okay, B, the only vector common to W in the orthogonal component of W is 0. And then C, the orthogonal component complement of W of the orthogonal component is W. Okay, they're orthogonal to each other. Okay, and then the last page. I think I'm just reading through these. Yeah. Okay, so theorem 4.8.9, if A is an m by n matrix, then the null space of A and the row space of A are orthogonal complements in Rn. Okay, the row and the null space are orthogonal complements. Okay, B, the null space of A transpose and the column space of A are also orthogonal complements of Rn. Okay, and then we have all this, but if you notice now, I even added 2 more to it. Okay, and these state the orthogonal complement of the null space of A is Rn, and the orthogonal complement of the row space of A is the 0 vector. Okay, and that is it for section 4.8. Okay, thank you. See you later.